In this video lecture, I will discuss the post-selection inference or PoSI method. This method was proposed in 2013 by Beck et al. In a very influential paper, which takes a much more general perspective than what we have been doing so far. So they start from the point of view that any kind of model selection affects your inference, and they want to come up with a method that tries to take this into account. Now, there are different ways in which we can have model selection. And what we've so far been doing is focusing on category 1, where we do model selection according to a pre-specified, well thought out criterion. And we can do that in a fully automatic algorithmic way. We can write down an algorithm in which the model selection occurs. So one, of course, prime example is doing the lasso, but also cross-validation or doing information criteria fall under this category. Now, this is model selection that we think carefully about, that we design explicitly, and that also makes it a bit easier to take it into account when we try to correct for that, because we can actually, in those cases, use the method and the properties of the method to come up with solutions. But there are two other categories that are also part of model selection that this paper also wants to take into account. So the second category, what you could call subconscious model selection, is the kind of model selection that everyone does, but that is hard to write down in a formal way, and that's much more an informal, intuitive kind of analysis. Well, when you start with your problem, you collect your data set, and probably the first thing that you're going to do is just inspect your data. Maybe you'll make some plots of your data. And maybe there are some series which look strange, and because they look strange, you decide to leave them out of your analysis. Then there's a whole bunch of preliminary analysis that you do. You start playing with your data, start estimating some models, and so on. Now, all of this goes in a fairly informal way, and we cannot hope to write that down in a formal algorithm and derive the properties of that algorithm. So this is much harder to catch, but of course it also has an impact on your inference. And then there's the third category, which I hope we all don't do, but it definitely exists, which is, well, in the best cases you could call it ignorant, in the worst case you could call it malicious, where we're actually doing model selection in such a way to push towards the results we want to find. Things like significance hunting or p-hacking and so on. It's probably the worst form that you could have is you want to show that variable A has a significant effect on variable B, so you try all the possible models until you reach one where the effect becomes significant. Now, this is obviously a category which probably has the largest effects on the properties of your inference, and you should really want to correct for that. But of course it will be quite ambitious to correct for even such bad practices. So what we've been doing so far requires knowledge of which model selection did we perform, and therefore you can only go category 1. But, well, we don't just want to do that. We want to do category 2, but mostly to protect against ourselves, because we all do it, and it's unavoidable, right? There's no way you could avoid that. And we actually also want to protect against category 3, because obviously category 3 leads to bad science. So what they do is come up with a method that is able to safeguard against all forms of model selection. So that includes p-hacking. And this, of course, is great. And, well, it's wonderful. But there will be prices that we have to pay in order to do that. So it, of course, does not come for free to have a method that can actually safeguard against p-hacking. And so the first price that we have to pay is that we cannot hope to do inference on the true teach P. And this is a big price that we have to pay. So what they take in the paper, what they call is the submodel view. And the submodel view says you don't make an attempt to recover true underlying relations. So if you think about a structural model which describes actual causal relations between variables, that is obviously independent of which particular model, which variables you are looking at. Now what they say is, well, we have to let that go and instead go for a more realistic goal of looking at models describing relations between variables within a specific model. So that means depending on which variables you include in your model, you actually get different parameters. Because we're saying, well, how are variables y and x1 and x2 related, given that only those are included, and not x3 and x4? And that actually means what we're looking at in the linear world is simply projections. So we're going to project y on the space spanned by the variables x. And that brings me to a more formal way of how we can actually interpret that. Now let's first take a bit more general perspective and say, well, we don't assume a true model anymore, so that's going to be similar to what they do. And then we're just going to try to find a way in which we can best use the random variables in x. So suppose we have p random variables, and we want to predict now y using those random variables, and we want to see what function of the axis does it in the best way. Well, if we want to define best, we obviously have to make a choice on what criterion are we going to minimize there. Well, let's take here the mean squared error, which is a logical criterion to take. So we want to minimize the squared expected distance between y and this function of x, this function g. Well, we can in this case solve that with a small trick fairly easily by inserting minus the conditional expectation of y given x and plus the conditional expectation. Well, write out the square then, and you'll see that the cross term is vanishing, and you'll end up with just these two terms, where there is no g in this first term, so we can choose g whatever we want. This first term will not change. The second term is always going to be greater or equal to 0, because there's a square. So the best we can do is make this 0. Well, we of course make this 0 by taking g of x equal to the conditional expectation of y given x. So if we want to minimize mean squared error, the best predictor that we can choose as a function g of the axis is the conditional expectation. And here of course you see that depending on which variables are in x, your conditional expectation will change. So here your model will change if you put different variables. For instance, if you add variables in x, you'll get a different outcome here. And well, this is typical of the sub-model view. So here we would take our sub-model would simply be, well, given that we include those x's, our model for x given y is modeled through the conditional expectation, which does not say anything about the true underlying relations, obviously, because there might be relations with other variables that are actually not in this x, for instance. Well, one example of is then if you assume normality, so assume we have multivariate normal for our x's and y's. So there we have covariances, we have a covariance matrix for the x's and the variance for y. Well, then we know that if we condition on x, y on x, we get this formula for the conditional normal model. And we actually see if we rewrite that, and we call this whole thing alpha and this whole thing beta, then we get the linear model. So if the data actually come from a normal, multivariate normal distribution, the conditional expectation is just a linear combination of your x's. So here you see in particular that well, this clearly depends, of course, on which x's are actually included. And it also, the coefficients actually depend on the underlying structure here of data. So if you would have different data with different properties, then also your beta would change. So this beta is not a true parameter. It's really a parameter only which only has context within this particular model. Now there's of course a practical problem with conditional expectations, and that is that we don't know what their form is unless we actually assume a distribution on x and y. So one thing you can do instead is, well, go one step further and say, well, instead of modeling the conditional expectation directly, which we don't know, we model a linear approximation of that thing. So we're going to model a linear function of your axis. Well, this is, of course, could be a good approximation or a bad approximation, but as always is an appropriate, valid approximation. Well, in that case, we can derive, instead of the best predictor, the best linear predictor. So those coefficients beta, which give you the best linear approximation of y. Well, that can simply be solved, again, by minimizing mean squared error. You probably see the parallel to least squares, and of course you can solve things in the same way. So this is just a simple minimization problem. You can write out the square, take derivatives, and you'll end up with this expression for the best linear predictor, which is essentially the population counterpart of the least squares estimator. So we have the covariances between x and y times pre-multiplied with the inverse of the covariance matrix of the axis. So again, we've come up with a model for y given those particular axes, and the associated coefficients then, of course, are subject to which variables are included in your vector xi. Now the nice thing about this is that this is always appropriate. So we can always define the error term. Well, of course, that's just a definition, but this error term will have mean zero, and even more importantly, the correlation with the axis will also be zero. So you will have a valid linear regression model. So this defines a linear regression model, and we know in this case that we can estimate this linear regression model because, well, there's the orthogonality between x's and epsilons. Now, of course, the reason why we can is because we defined it as such. So we're looking for what is actually in the appropriate linear regression model for these y's and these x's. And again, these coefficients do not have like a true causal structural meaning. They only have meaning within that particular model. And of course we see, well, they directly match up with least squares, where least squares really estimates these parameters. Now, so far I looked at random design. Now let's look at fixed design, because it requires a small modification. So assume your x's actually are deterministic. Well, then we cannot treat each pair the same, and instead we have to average over all of the pairs. So this is a slight modification, but in that case, well, again, the same arguments give you the best linear predictor. And in fact, it now even looks more like least squares with deterministic axes. Now, the nice thing is, as I mentioned, this whole thing always has a meaning. And it's always a valid representation of your data, even though your true data generating process does not even have to be linear in X. Well, we also don't assume that the linear model is a good approximation. That is, for instance, what we did when we looked at the post-double selection paper and also the other papers by Bologna et al., where they say, well, we take a nonlinear model and we assume that we can approximate that well with a sparse linear model. There we needed the approximation to be good, so the remainder term had to be small. Here, we don't care at all about that because we take the coefficients at face value. We say, well, given that we included these variables in X, and given that we fit a linear model, well, this is simply the best we can do. And we don't look any further than that. That, of course, does mean that you have these betas which are changing depending on which variables are included. And so if you change the composition of your explanatory variables, you will also change what your beta looks like. And that means that this beta only has the meaning within this specific model. And this is exactly the submodel view that they have in the paper. So how they write it is as follows. they say, suppose we have data from a normal distribution, and every point in the observations has its own mean. So we have a vector of means of the same length as the vector of data. We're not saying where these means are coming from. So it might be that those means actually are linear combinations of x's and betas. But, well, that's not what we're assuming. We're not assuming any model here. We're just assuming, well, we end up with y's from a normal distribution with a vector of means mu. Well, how these means come about, if that's a linear of x's or a non-linear function of x's or whatever, we're not saying anything about that. So the only thing we're saying is observation yi has mean mu I. We do have predictors, right? Of course, we do have x's. We have x1 up to xp, possibly large, so p can be larger than n. So this is a high-dimensional, a possible high-dimensional framework. Then, well, given that we don't have a model, we cannot even take a structural view, as we did, for instance, for the post-double selection and these sparse-flat lasso. So the only thing we can do is take the submodel view, where we say, well, given a set S, which indicates which variables are included in your model, we have a corresponding vector beta S. So this is just a projection of the y's on those xs's, or in other words, the best linear predictor given those variables in S. And it has this particular form, and here we plug in, of course, the vector of mu's. Now, the crucial thing to realize, and that is really what is the main difference between what we've been doing so far, is in the submodel view, you have, by construction, no omitted variable bias. Because if you omit a variable, well, your parameters will change. They will adapt already to that omitted variable. So if your true model includes x1 and x2, and now you delete x2, then the coefficient of x1 is going to change to take into account the correlation with x2. So you basically are assuming away omitted variable bias, or you're choosing not to see this as a problem. And that is, of course, in stark contrast to what we did so far, where we looked at the full model view, where we say, well, we have some true model for your y's. There's a true vector of coefficients of beta, or it's a good approximation to the truth. And then we were trying to see, can we recover that? Well, we looked at those methods before. Of course, you can argue what is the better approach to take. This is, of course, very much a philosophical issue, and it depends on the kind of application that you're after. So you might say, well, I want the truth. I want to have these true coefficients because they matter. Right? They are the ones that we're after. Now, of course, you can also argue how realistic is it that you anyways can capture true coefficients with such a simple linear model. In what kind of situation will the truth really be something like this, a linear model, and you have true coefficients, and everything is great? So obviously the truth is going to be much more complicated. So why should we take this full model as a good approximation of the truth, but submodels not? That is, of course, debatable, and there's no right or wrong answer. So you could say, well, the full model is really, it's too much to ask for, so it's unrealistic. And we should be much more realistic and focus on submodels, which is always valid, and we sort of recognize, no, we're not really, this model is not the truth, we're explicitly recognizing that. But maybe we're also then not ambitious enough, because maybe we're too satisfied too soon. That's, of course, another perspective that you could take on. And for instance, if you really want to make statements about causality, this is going to be very difficult in a submodel view. Well, if these parameters don't have any causal meaning, then of course that massively complicates such an analysis. So I'm not going to take a stance here on what is the better approach. I'm just pointing out the differences between these approaches. Well, and saying that in fact, if we want to be as general with the PoSI as they want to be, you have to take the submodel view. So what of course then is the problem, you might ask, given that as we discussed last week, the big problem was omitted variable bias. Is there anything left to solve, or have we just assumed away all our problems? Well, of course, there is still things that are left to solve. And that is in particularly the uncertainty that we're not taking into account. The fact that we search over all models creates, of course, uncertainty because, well, the data are random, so the model is actually random that we're searching for. And even irrespective of omitted variable bias, this is still something you would not account for when you do what I call here naive inference or oracle inference. So this problem is what is addressed with the PoSI method. Now again, there are people who agree and disagree with, and there's, for instance, another paper, I also put the link on Canvas, which says, well, once you deal with the omitted variable bias via the submodel view, actually that solves most of your problems and naive methods work fine as well. I'm not sure whether that is maybe also a bit too simplistic argument, but of course there is some truth in that. Nevertheless, what is of course really cool about the PoSI method, and there's no other method that we looked at so far which does something similar, is that it accounts for any model selection and even the bad ones. So even the ones where people were doing p-hacking and trying to go towards significant outcomes that they want to have. So let's see how it works. First, what are we actually estimating? Well, if we take a model S, so the S indicates the variables that are included, well, that we can then of course estimate by least squares, assuming that these models that we select are of relatively low dimensionality. Now, we can express the distribution of the least squares estimator using the submodel view. So we write y as mu plus something which has a normal distribution with mean 0, say a factor z. Well, then you can of course plug that in. You get the coefficient, which we defined because it's the projection coefficient, as just this thing, which is beta s. And we have something which is normal. And well, here we just can derive the variance of this term, and that will of course be the standard least squares expression. So even with the submodel view, we get the same distribution as we would get normally, where we would not even take the submodel view. Of course, it depends on the particular model. So within that model, of course, your estimator is unbiased. Now let's go a bit further and see then how we do inference. So we take the jth element of the vector, the variable j. Now note that this is not always defined. But if you would take a variable j which is not an s, then well, this of course this coefficient is not defined. So even there already indicating this is tricky in this kind of model selection view. But so we define this beta j s, and then we want to do inference on that parameter. We'll take standard definition of a residual maker matrix and let all other variables in model S except variable j be denoted by x s excluding j. Then what we can do is, in typical Frisch-Walk style, as we have already been doing before, is we can partial out the effects of the other variables. So we're going to regress x as j, the jth column, on the variable, on all the other variables. So there's a j missing here in this xs. So we take the jth variable and then we regress it on all the other variables. And the same we can of course do for y, regress it on other variables. Well, then we know by the Frisch-Walk theorem that if we then regress the residuals of these two regressions on each other, that would be the same as just doing the regression of y on all variables in xs. And therefore, we can express the least squares estimate as exactly in this Frisch-Wald kind of style. Now the reason why we do that is that it just lightens notation a bit, and we can in fact simplify everything by writing the least squares estimator in this form, where we do the inner product of y and the residuals from the regression of variable j on all the other variables in S, and we divide there by the squared L2 norm of that same residual vector. Well, and then we know that that thing has a normal distribution simply by the properties of the least squares estimator, and we can do a t-test on that. So that would be a standard t-test. One thing, of course, to take into account is that we also need to estimate the variance here. And now this is going to be an important thing for this method, so we should be able to estimate the variance, or here the standard deviation, of the error terms without relying on model S. So that is complicated, because I mean the most natural way would simply be regress y on xs, take the residuals and get the standard error estimates from there. But that would of course make it model dependent, and we need it to not be model dependent. So one thing you could do if P is not too large is say, well, I'm estimating always the full model and then getting the residual variance from that. If not, well, then it's going to be quite complicated. But we do need that assumption for now. And in fact, what we're going to assume is that this thing has a chi-squared distribution. Now, suppose we have all this, and suppose that your set x, the variables which you include, is fixed. Well, then this t-statistic would just have a t-distribution. Right? We have a normal and we have your chi-square, so this will end up with a t-distribution. It does not mean that you need to include all variables, it just means that S should be fixed. So you should decide, without looking at the data, which variables to include in S. Well, if you did that, you could use the t-distribution, and for instance, you could do confidence intervals in an entirely standard way, where your coefficient that you put in here for k, the value that you put in there, would just be a cutoff point from the t-distribution. So you take the alpha over 2 cutoff point from the t-distribution, and in that case, you would get a 1 minus alpha confidence interval. But now, our S is actually S hat. It's going to be the result of doing model selection on the data. So this is going to screw up, even though we do not have the omitted variable bias, it is going to screw up because this t-distribution will not be appropriate anymore. Because this assumed that you actually fixed S beforehand. Now, denote S hat as a function of y to indicate that it's actually a model selection doing on y, and we can write it as a mapping which finds this model from all possible models. Well, if you have p variables, then each variable can be in or out of the model, so you have 2 to the power p possible models. S hat picks one of those models based on the data. Now clearly this is random because it depends on the data. But that also means that your coefficients, your parameters, which we assume normally to be fixed, are random themselves. For instance, even the dimension is random. So the length of the vector is actually random because it depends on how many variables are included in your selected model. The question, the event whether variable j is in S hat is also random, because it's again the result of the model selection procedure. And even if we would condition on j being present, then still your parameter is random because, well, the other variables are not fixed. So the other variables can still actually change them. So we need to take this into account, this additional randomness. Now there are 2 ways in which you can think of doing that. Perhaps the most natural way is to condition on the fact that we selected a certain model. So can we come up with a probability that our confidence interval that we want to construct covers our true parameter, given that we selected a particular model? If this holds for all possibly selected models, then we have, of course, a valid way to do inference. But while this is perhaps more intuitive, it's also much more complicated because we need to explicitly condition on that, and therefore we need to know how was your model selected. Well, and that is the thing we don't want to do with PoSI. So PoSI takes a different approach, and it says, well, instead of conditioning, let's look at it unconditionally, but let's have this probability that our selected confidence interval for selected model covers the true parameter for the selected model for all variables in your selected model. And here comes the key part: over all possible selected models. So we're going to do inference over all models at the same time. So this very much resembles what we did for multiple testing, where we look at controlling probability of making rejections or false rejections over all possible variables. Now this, of course, is a big ambitious statement if you want to control this. In particular because you still have this randomness in here, which is a bit strange. So, but there we can actually do something smarter. So here, instead of doing this over all these random models, we can do it over all possible models in general, because clearly any model that can be selected is included in the set of all 2 to the power p models. And therefore our cutoff points, we know that if we look at the maximum over j in a certain selected model, is always going to be less or equal than the maximum over j in any fixed model, but maximizing over all possible models. Well, that we use to define a new constant k, which we use in our confidence intervals. So this is called the PoSI constant, which is the smallest k such that if you take the maximum over all j in a certain model and then take the maximum over all possible models of your t-statistic, absolute value of the t-statistic, then we want the smallest k that makes this thing small or equal to k have probability at least 1 minus alpha. So we're controlling over all possible models all of the t-statistics that you can take. And that means that for the selected model, of course, it also holds, because the selected model is going to be one of the models that we're actually maximizing over here. So we can then actually see that if we can construct this PoSI constant like this, we're guaranteed to have valid intervals for our selected models. And it holds, of course, irrespective of which model is selected and which variable we're actually looking at in a model. Well, that's all nice and well, but of course what remains is how do we actually calculate that constant? Now what you essentially have to do is you would have to simulate over all models. So you would have to look at all possible t-statistics for all possible models and then do a simulation study based on those, how large that constant should be, which of course is extremely computer intensive. Now what they do in the paper, and they spend a large part on that, is actually coming up with tricks to speed up the calculation. So rather than having to do all of these calculations manually, they come up with shortcuts that you can take because of the Gaussianity. But regardless, you still need to do simulations. So have more look at the details in the paper, or I think that would be recommended, use the R package that they provide. Now, nonetheless, these speed ups, if P is very large, you do actually need to do a lot of calculations, and they do get costly quite quickly. So the package also in that case becomes quite slow. Now, what you can do, of course, is somehow put some structure on the problem. Maybe you do only nested models, or maybe you only want at most d variables in your model, where d is a lot smaller than p. Well, if you do that, then of course you speed up the calculations, because you don't need to search over all possible models, but only those models which satisfy your structure. So let's wrap up the PoSI method. So the idea is very interesting. It's about guarding against any form of model selection that you can do. There are of course also some limitations, and the first is that as it's originally designed, this was really fixed design and normality, which is of course rather restrictive. Now people have considered extensions, so it is possible to extend it, but that of course remains a tricky part. Now, in practice, what we also see, and that is I think quite important, is that intervals tend to be quite wide. So they are wider than the lasso-specific methods like post-double selection or desparsified lasso. This of course makes sense, because what we are doing here is valid under any form of model selection, and not just the particular lasso kind of model selection that we can do. Well, and then of course there's the big thing that we discussed in details, is the submodel view, which it makes interpretation maybe more complicated than if you would have the full model view with causal parameters. But against all these downsides, there is also one massive upside, and that is that you can apply this method to any published research results afterwards. So the only thing you need to have is access to the full set of data that people looked at. So if you have the full set of data that people looked at, you don't need to know anything about how they ended up with their final model. You could just apply PoSI and compare the interval that you get to what they get out. And this of course makes it quite important if we think about where I started off this inference session with the whole debate about replicability of empirical findings, of how to see p-values, how to guard against people either intentionally or subconsciously guiding their methods towards significant results. Well, PoSI is one way to approach that. Of course, it's not the only way, and it's not without its problems, but it's something you can always slap on afterwards on any published result. And I think in that sense it could really have a lot of importance in academic research. Now, despite its generality, given the fact that it has also these downsides, well, submodel view, but also in particular computational issues, it's not extremely popular in practice. So we'll be looking at some alternative methods that in a similar vein are also used to guard against model uncertainty.